So the question over here says, if E equal to 6I plus 3J plus 4K, that's our electric field vector. Calculate the electric flux through a surface area of 20 units in YZ plane. If there is a plane which is YZ, let's suppose this is our YZ plane, Y axis and Z axis, then the perpendicular to YZ plane, we know the normal to this plane is X plane, X axis, right? So we will say that area vector, the normal to the area will be 20I cap, right? So we can find the flux phi, that will be equals to E dot A, and unit vector, which is area. Be very careful, area is a scalar quantity, but here this I cap denotes the normal, right? We have done that in the previous lecture. So E will be simply 6I plus 3J plus 4K multiplied with 20 I cap. So if you multiply, we know that I dot I, it will be 120, and flux is a scalar quantity, and the unit will be electric field as a unit of Newton per Coulomb, and area is meter square. So it will be Newton per Coulomb meter square. Okay. So the question over here says, if E is equals to 8I plus 4J plus 3K, calculate the electric flux through the surface area 100 units in XY plane. So if it is XY plane, so this plane is X and this is that's a X axis, and this direction is Y axis, right? So perpendicular to XY is Z axis. So the normal will have a K cap, right? So we can write here area vector. Be very careful, area vector here will be 100, and K cap denotes here the normal vector, normal to the area. So our flux phi will be equals to E dot A, and that will be equals to 8I plus 4J plus 3K multiplied with area vector, that will be equals to 100 K cap. So that will give us how much? 300 Newton per Coulomb meter square. That's our unit. Okay. We'll move to the next one. So question over here says the electric field. Let me write the electric field here. E, which is equals to 5I plus 4J minus 4K. Let me keep it in a bracket into 10 to the power 5 Newton per Coulomb, and the area here again given in terms of vector, that is 2I minus J cap into 10 to the power minus 2. Again I am repeating, this is our area is the normal. So if it is in normal case, phi will be equals to the dot product of E dot A. So here it will be 5I plus 4J minus 4K multiplied with 2I minus J multiplied with into 10 to the power 5, and I am just keeping the powers together, right? So now let's do the dot product. So 2I into 5, 10, and J with J minus 4, and multiplying 10 to the power 5 into 10 to the power minus 2, 10 to the power plus 3, and that will be equals to 6 into 10 to the power 3 Newton meter square per Coulomb. That will be our unit. So that's answer is 6000 Newton meter square per Coulomb. So the question over here says a circular plane sheet of radius 10 centimeter. So R is nothing but 10 centimeter. So we can just simply write it as 10 to the power minus 2 meter, right? It is placed in a uniform electric field. So our electric field E is nothing but 5 into 10 to the power 5 Newton per Coulomb, making an angle theta as 60 degree with the field, right? Question says calculate electric flux through the sheet. So if we try to draw this is our circular plane sheet, and the electric field is making, let's say the electric field is making here, this is our E, making an angle of 60 degree with the sheet, right? But we don't need this angle. What we need is our angle must be between electric field and normal to the circular sheet. So this is our N cap, and if this is 60 degree, this will be 30 degree. That is obvious. Why? Because the normal is 90 degree to the sheet, right? So that is 30 degree, and so let's use the formula. Flux phi will be equals to EA cos theta, correct? So E is nothing but 5 into 10 to the power 5. Area is pi r square. So we will write it as 22 by 7 into r square, which is 10 into 10 to the power minus 2 into 10 into 10 to the power minus 2 into cos 30 degree. So cos 30 is nothing but root 3 by 2, right? So what we will do here is let's multiply them. So let's multiply the powers first. 10 to the power 5 and 10 to the power 6, and 10 to the power 6 and 10 to the power minus 2 and minus 2 4. So 10 to the power 2 we left with, right? And let's multiply 5 into 22 by 7. So that will be 15.714. Well, let me repeat again. 10 to the power 5 and 10 to the power 6, 10 to the power 6 minus 2, 10 to the power 4, and minus 2 is no, it's fine. Exactly, yes, it should be 10 into 10 to the power minus 2, correct. So 10 into 10 to the power minus 2, that's a small error. So here if you make this, that will be 10 to the power 3, and cos 30 is root 3 by 2, right? So let's multiply this value. Root 3 is, I am taking 1.7, so that will be 26.7 divided by 2, that will be approximately 13.35 or 36, let's make it 10 to the power 3 Newton meter square per Coulomb. That's our answer. Any doubt? We'll move to the next one. Over here says, consider a uniform electric field. So let me just write here electric field E, that will be equal to how much? 3 into 10 to the power 3 I cap, right? Which means it is along x-axis, Newton per Coulomb. Calculate the flux of this field through a square. Square it is given. So area, directly area is given. So it is 10 centimeter square. Let me convert it into meter square. 10 into 10 to the power minus 4 meter square, right? Now this is the data given. The first part, it says its plane. The plane of the square is parallel to YZ, which means our normal will be along x-axis, right? So our area vector, we can make it as 10 into 10 to the power minus 4 I cap, right? Sir, what if it was not along x-axis? Straight away 0, because if the normal is not along x-axis, straight away the flux will be 0. So we can find flux phi, that will be equals to E dot A. So that will be 3 into 10 to the power 3 I cap into 10 into 10 to the power minus 4 I cap, dot product straight away. That will give us how much? 30 into 10 to the power minus 4 and 3, that's minus 1, and that will be 3 Newton meter square per Coulomb, right? Now that's our first part. Second part, be very careful. It says the normal to its plane. Normal to its plane. Normal to its plane means, let's assume that this is our normal to its plane, right? N cap is making 60 degree with the x-axis. Okay. That's fine. That's fine. We are not focusing on that. I'm just finding the direction first. So N cap. Yeah, that's a centimeter square, no? So centimeter square, if you convert, it is meter square. See, 1 centimeter is 10 to the power minus 2 meter, right? So 1 centimeter square, that will be 10 to the power minus 4 meter square, no? Squaring both the sides, right? Okay, let me come back to the second one. Understood the first part? Yeah. So the second one, the normal to its plane. So if this is the normal, it makes 60 degree with the x-axis. So let's say this is our x-axis. So along x-axis, it is making 60 degree, right? And we are given directly that our electric field is also along x-axis. Look at this I cap. So angle between which we are taking electric field and the normal, right? So theta is straight away will be here 60 degree. Be very careful. It won't be 30 degree in this case, right? So flux phi will be equals to EA cos 60 degree. In this case, second part, E into A, we already found it in the first part, which is 3, and cos 60 is 1 by 2. So in that case, it will be 1.5 Newton meter square per Coulomb. Any doubt? Let's see the problem. The question over here says, given a uniform electric field. Now electric field E is given over here as 5 into 10 to the power 3 I cap. I cap is our x-axis, right? And find the flux of this field through a square of side is given here. So side length L is 10 centimeter. Let's put it here as 10 into 10 to the power minus 2 meters. So let's calculate area over here only. So area will be square of this L square. So that will be how much? 100 into 10 to the power minus 4 meter square, right? On a side whose plane is parallel to YZ. So let's assume that it is parallel to YZ like this. This is our parallel to YZ. So this is our y-axis, and let's call it as z-axis over here, yz. So perpendicular will be where? It will be along x-axis, right? Okay. What would be the flux through the same square if the plane makes 30 degree? Read the question very carefully. The plane is making 30 degree with the x-axis. So if the plane is making 30 degree with the x-axis, the normal will make how much? 60 degree, right? Because we always take the angle between normal and the x-axis, right? Normal and the field, sorry. So field is along x-axis, so theta will be 60 degree here, so flux phi will be equal to EA cos 60 degree, right? So electric field over here will be how much? 5 into 10 to the power 3. Since it is along I cap, so area I am just keeping it along I cap only, 10 to the power minus 4 into cos 60, which is half. So let's make it as 500 into 10 to the power minus 1 whole divided by 2. So that is 250 into 10 to the power minus 1, and that is how much? 25 Newton meter square per Coulomb. Theta is very confusing because you are not reading the line properly. And it will confuse because it confuses everyone. So be very careful. You have to read it at least 2 or 3 times. And just keep in mind that one thing, we always find the angle between normal and the electric field, not between electric field and the area. Yes, so whenever you read the question, just recall this concept that you are looking for angle between normal and the electric field. And read again the question and see if it is given. Like in this case, it is clearly saying that flux through the same square if the plane makes an angle 30 degree, not the normal to the plane makes an angle of 30 degree. If instead of plane, if they say normal to the plane makes an angle of 30 degree with the x-axis, then it's fine. Okay, straight away that angle. Understood? Okay. So let's see the last part of this chapter, that is our Gauss law. Okay, so let me just write here Gauss law. Very important part because that one derivation might come from this part. Either they will give you the question from dipole, the derivation, equatorial or axial plane, or the derivation will be from Gauss law. Let's understand what is Gauss law. So let me write the definition of Gauss law. Very important, don't make any change in this particular definition. Okay. So according to Gauss's law, according to the Gauss's law, the total electric flux coming out from a closed, I'll explain each and every word, okay? So keep patience, just write the definition first. From a closed Gaussian surface will be equal to 1 over epsilon naught times the total charge enclosed by the surface. Very, very important for our numerical problem, as well as the two or three derivations which are related to Gauss law. Now let's focus on the statement, what this statement says. Very simple and very important it is. Gauss's law says that the total flux, this is another way of counting flux. What was the first method? We have already discussed in the previous lecture. Phi was equals to E dot A n cap dot product, or you can simply, if you are given with the formula, E A cos theta, or the third way we found it as integral of E dot dA, that we will use here to derive some expressions, right? So these three methods we have already discussed. Electric flux. Another and simple yet very powerful way of finding electric flux is Gauss's law. So according to this law, the total electric flux coming out from any closed Gaussian surface. Now as a beginner from 12th standard, many means mostly 99% people, they have a problem with this word, Gaussian surface. Sir, what is a Gaussian surface? How you define a Gaussian surface? Is there a way we can define a Gaussian surface? We'll talk about that thing. It's always equal to 1 by epsilon naught times the total charge enclosed by the surface. Now first thing, to be a Gaussian surface, it should be closed. So closed can be like this, yeah, enclosing the charge. Can this be a Gaussian surface? No, because it's an open surface, right? So Gaussian surface, it should be closed, first thing, and it can be any random surface, but from 12th standard you have only 3 types of Gaussian surface which we will consider. First will be spherical surface, second will be cylindrical surface, and the third one will be cubical mostly. We'll not talk about any other random surface, okay, because we are dealing 12th standard only symmetrical surfaces, right? So if you imagine some charge plus q, minus q, 2q, 8q, any random set of charges, you can imagine a surface around it that is purely spherical, okay. So when to imagine cylindrical and cubical, that is also very rare. We will see how those situations, okay. So any surface that encloses and it is closed surface is known as Gaussian surface. So don't think much about Gaussian surface. They are just mostly spherical, and rarely we will think of cylindrical or cubical, okay. And how do we express this Gauss's law in mathematical form? It is given by flux phi will be equals to total charge q enclosed. I am writing the specific word En. This is very crucial while dealing with the numericals. So mostly people, they remember this as q by epsilon naught, but it should be q enclosed by epsilon naught. That is our flux. So from where this expression arrives, we will derive it. We will find the proof of this Gauss's law within a minute. So any doubt up till here? So let's see how we got this expression. So proof of Gauss's law. Let me write here proof of Gauss's law. So let's imagine that, yeah. Can you repeat your question? See, sometimes the question, they can give you a simple question for 1 mark, define Gauss's law. In that case, you have to simply write this definition which I have given you and write this particular mathematical relation, right? But if they give you the same question for 2 marks or 1.5 marks, sometimes you have to give the proof also, because proof is not that large. It's a hardly 2-3 steps, right? So if they are giving you in higher weightage question, you have to give the proof. If they give you in hardly 1 mark definition, then you don't have to do the proof, okay? So let's see what is the proof according to Gauss's law. Let's see, plus q. Let's assume a charge plus q. And if you imagine the field lines, they are going radially outward and they are around, we can imagine a Gaussian surface, a closed surface which encloses this charge, right? So if the field lines are going radially outward like this, okay, around this charge, all over here, then we can imagine a small area, a very small area, and see how many field lines are passing through this area outward, okay. So this flux phi, we know that it is equal to E dot area, right? Let's put an integration E dot dA, that will be the total flux coming out of this, right? Now electric field at any point away from this charge at a distance r, we know that we have learnt it in the previous lectures, 1 by 4 pi epsilon naught q upon r square, right? Integration of dA. And integration of dA gives us that, you will learn it in maths 12th standard chapter 8 application of integrals. So for the time being, just remember that sir is going absolutely correct, okay. So integration of dA will give us, let me just take the constants out, 4 pi epsilon naught r square, and integration of dA from maths will give us the total surface area, the outer surface area of this sphere, and that is nothing but how much? 4 pi r square. So this, from where this arrives? Maths, integration. So there you will understand how integration of a sphere area will give you 4 pi r square, and if you are dealing with a circle, it will be pi r square. Be very careful, there is a difference between sphere and circle. So don't get confused between that. So flux phi will be this. Let's cancel out 4 pi with 4 pi and r square with r square. We got our flux phi as q, which is enclosed in this surface, upon epsilon naught. So this is our proof of Gauss's law. Yeah, this is small. That's why I said if they'll ask you question for 1.5 or 2 marks, simply add the proof so that you get complete marks, okay. Many students, they simply write the definition, but definition is only for 1 mark, okay. Then I'll move to the next one. Okay, now depending on Gauss's law. Now the question is, sir, what is the use of Gauss's law, so that you can understand the application better. See, Starting from the very beginning, I have told you the chapter is based on two types of charges, positive and negative. Then I discussed about Coulomb's law. But I also discussed what are the limitations, where the problem arrives, though it's not, we can figure out, but the problem is Coulomb's law at a time takes two charges. Then we found the concept of field. And then we discussed how we can find the field for a dipole or on equatorial or axial plane. But to find field, you should know flux, because flux is E dot A. So if you can somehow find the flux, you can easily find the field. So Gauss's law basically focuses on finding the field. Okay, so because if you know the field at a point, you can easily figure out the force at that point. Okay, so there are different applications. Let me write the first application. The first application is field due to an infinitely long straight uniformly charged wire. So let's say if I assume a wire, straight wire, okay, and this wire is completely charged, let's say. So let me make it so that I can show the charges. Okay, one second, let me just redraw it. Okay, so let's say the charge on this wire is positive, all over positive. Sir, can we think of negative? Exactly, you can think of negative also, doesn't make any difference, you'll get the same thing. Sir, but it is saying infinitely long wire, so wire is very large, okay, and if you think of a spherical Gaussian surface, it will not be able to enclose it, right? So here we are forced to think of a cylindrical Gaussian surface. So let's say this is our cylinder, okay, let's say this is our cylindrical Gaussian surface, okay, and we are finding the flux due to, okay, the cylindrical Gaussian surface, and the electric field due to this wire will be radially outward in all the direction, right? Yeah, radially outward because of positive. Let's assume that Gaussian surface here is having a position R, right? Sir, can you imagine a bigger Gaussian surface? Yes, you can. Sir, how you decide which size you can? See, if you are looking for electric field at a point, let's say this point, so you have to decide your Gaussian surface according to that, right? So large, if you are looking for electric field at this point, you can imagine a Gaussian surface of this size, correct? Okay, so the flux is coming out from the curved surface area of the cylinder, because here this is perpendicular, right? So no flux. Theta will not contribute here. The flux will not be contributing here. So we can say that flux phi, here, one second. Flux, one second, it's reloading. Just give me, okay. So we can imagine here flux phi, that will be equals to how much? E dot A. Any doubt in this part? Because we know this from previous lecture, flux phi is E dot A, correct? Now, we know that if we integrate this area will give us curved surface area of the cylinder. So R is radius, and let's assume that L is the length of the cylindrical Gaussian surface. So flux phi will be nothing but E dot 2 pi RL. Any doubt in this part? Flux phi from Gauss's law. We know that from Gauss's law, flux phi will be total charge enclosed Q in upon epsilon naught. Now what is Q in? So Q in will be the charges which are in this section of this cylindrical Gaussian surface, right? So be very careful, we will talk about that thing within a minute. So E into 2 pi RL. But sir, how much is the charge present in this section of the Gaussian surface? For that, let me remind you a concept we learned in the previous lecture, that is lambda. What is lambda? Linear charge density, and that gives us Q by epsilon naught. Q by L, sorry. So what is Q? Q is the charge enclosed in that small section. So length we are taking this L, not the complete length of the wire. L is that section of the wire. So Q will, yes, so Q in will be lambda into L. So let's substitute here lambda into L upon epsilon naught. That will be equals to E into 2 pi RL. Any doubt in this part? Let's cancel L with L. So electric field E, that will be equals to lambda by 2 pi R epsilon naught. Any doubt? Very important for problems. Direct question they ask in board exams.